All right, today we're going to tackle a huge question. How in the world do you build trust in a system that has nobody in charge? Well, the answer lies in four cryptographic locks that are really the foundation of technologies like blockchain. So let's dive right in. This is the big puzzle, isn't it? I mean, how can a network of computers all over the world agree on one single version of the truth without a bank or a government calling the shots? The answer isn't magic. It's just really, really elegant mathematics. And it all starts with our very first lock. So our first lock, it's all about creating a unique, totally unforgeable identity for any piece of digital information. The best way to think about it is like a digital fingerprint, and it's created by something called a hash function. So, what exactly is a hash function? Well, it's basically a mathematical meat grinder. You can feed it anything, a single word, a whole sentence, even the entire text of a book, and it squishes it all down into one single string of text that's always the same length. For systems like Bitcoin, the gold standard for this is an algorithm called SHA-256. It's the workhorse that keeps the whole ledger secure and consistent. Now, what makes these functions so powerful are three core properties that honestly feel a little bit like magic. They're consistent, meaning that the same input will always give you the exact same output. They're a one-way street, so you can't reverse engineer the original data. And they are incredibly sensitive to the smallest, tiniest change. This amazing sensitivity has a pretty cool name. It's called the avalanche effect. Just look at this. Change the capital B in Bitcoin to a lowercase b, and you get a completely different, totally unrecognizable hash. And this is so crucial because it means that if anyone tries to alter even one tiny character in a transaction, the digital fingerprint changes completely, making any kind of tampering instantly obvious. And what about that one-way property? I love this analogy from the source material. It's a one-way street. This pre-image resistance means it's just mathematically impossible to take that hash, that fingerprint, and figure out what the original data was. So the key takeaway here is data gets fingerprinted, and that fingerprint can never be reversed. Okay, so we can fingerprint data, awesome, but how do you actually prove that you are the one who owns that data? Well, that brings us to our second lock, creating your own unique digital identity using a pair of secret keys. This is all done through a system called public key cryptography. Now, the specific algorithm used in most blockchains has a pretty complicated name, elliptic curve digital signature algorithm. But the core idea behind it is actually pretty simple. It generates a pair of keys, one public and one private, that are forever linked through math. So, let's break this key pair down. Your private key. Think of this as the ultimate secret password. It's just a huge, randomly generated number that you guard with your life and never ever share with anyone. Your public key, on the other hand, is derived from that private key, and it acts like your public address or your account number. You can and should share this with anyone you want completely risk-free. And this is the absolute key to the whole system's security. The math behind it makes it super easy to generate a public key from a private one, but it is computationally impossible to go the other way. We're talking not even the world's most powerful supercomputers could crack it. This one-way function is the very bedrock of your digital wallet security. Okay, quick recap. We've got a fingerprint for our data, and we have a secret key that acts as our identity. Now, lock number 3 is where we combine these two to create something incredibly powerful, an unforgeable digital signature. This is how you prove you own something. The way it works is actually pretty slick. First, you use your private key to sign the transaction data, which creates a totally unique signature. Then you broadcast that transaction along with your signature and your public key out to the whole network. From there, anyone on the network can use your public key to check and verify that the signature is legit. And that verification step, that's what makes this whole idea of, true digital ownership actually possible. The math lets anyone prove that the signature could only have been created by the person holding that secret private key, all without you ever having to reveal the key itself. It's like signing a check with a special kind of ink that everyone can verify as yours, but absolutely no one can copy. Okay, so we can create transactions and we can verify them. But there's a problem. A blockchain has millions, even billions of them. How on earth do we manage all that data efficiently? And that brings us to our fourth and final lock, a brilliant data structure that works like a super smart filing system. And this is a really practical problem, isn't it? The entire Bitcoin blockchain, for example, is gigantic. We're talking massive. It would be totally impossible for your cell phone to download and search through hundreds of gigabytes of data just to confirm one little payment. The solution is this absolutely ingenious data structure called a Merkle tree. Here's the idea. Imagine you take every single transaction in a block and you create a hash, a fingerprint, for each one. Then you start pairing up those hashes and hashing them together. You keep doing this over and over, building up a pyramid of hashes until you're left with just one single hash at the very top. And that's called the Merkle root. So remember that massive, kinda scary file size we just talked about? Over 500 gigabytes, and it's getting bigger every single day. Well, get this. Thanks to the Merkle tree, to prove your transaction is inside that giant file, all you need is this tiny, tiny piece of data, a Merkle proof, that is often less than a single kilobyte. The efficiency gain here is just mind-boggling. And that incredible efficiency is what makes something called simplified payment verification, or SPV for short, possible. It's the core technology that lets lightweight things like mobile wallets securely check on transactions without having to download the entire history of the network. It's a total game changer. Okay, so we've looked at all 4 locks. How do they all fit together to create this amazing system of trust with nobody in charge? Let's put all the pieces together. So first up, you've got hash functions. Those are your tamper-proof digital fingerprints. Second, you have public and private keys, which give us all secure digital identities. Third, digital signatures let us prove we own things without giving away our secrets. And finally, Merkle trees file everything away so efficiently that the whole system can work on a global scale. Put them all together, and you've built a fortress of mathematical trust. You know, when you really boil it down, this isn't just about money or currency. This is a fundamental toolkit for creating verifiable trust between total strangers, and it's powered entirely by math. And that leaves us with a really fascinating question. If we can build trust without needing a middleman, what else can we build?